All right. So this is lecture 4, and let's see where we are and where we are going. So far, we have been discussing in the 3D. Last time we discussed 3D representation of forces, and we demonstrated how you set up the vector equation for a force, which is typically given by, if you have a force in a space, typically that force is given by 2 points, coordinates of 2 points acting along the direction of that force. So in order to find or set up the vector equation, you need to multiply the magnitude by the unit vector along that direction. But if you have been given, or you can find all the components of the force somehow, another option is also this representation. But anyway, we discussed that. But most importantly, in fact, we said that once you have the vector equation for all forces in 3D, the concept of resultant is what? Sum of all forces in 3D, if you want to find them, comes down to adding up all the x components to find the x component of the that resultant, sum of the y components of all those forces, and sum of the z component of all those forces. So that's how a resultant can be found in 3D. And if you have forces that act on a particle A, and you have several forces, F1, F2, F3, and so on. If this particle is in equilibrium, what that implies is that resultant of all these forces acting on a particle has to be zero, which means if the resultant is zero, all the components are zero. So we ended up with 3 equations and 3 unknowns that allow us to solve for up to 3 unknown forces given. So with that summary, I'm going to do at least one problem to demonstrate the application of these. We did a problem on the resultant. So what I will do today, I want to solve a problem of equilibrium. Okay, so let's do that. This is the problem I have selected from your book, and that is problem 2.121 from the book. Okay, so this is the problem. You do have a 4 cables that are attached to a ring at point A. Point A is located at 60 inches below XZ plane. In this ring, we pass a cable through this ring. This cable comes here, goes here, so, and is attached to these 2 points on the floor, on somewhere. Okay, so as the problem states, since this cable goes through the ring, forces in these 2 cables would be the same. In other words, force of AB is equal to the force of AC. But we tie 2 cables also to this ring and connect them to these 2 points, D and E. Okay, coordinates of these points are given. This E is at 45 inches from the origin. This is 80 inches from the origin, and B is 17.5 inches, and C is given at 25 inches. So at, we know that a known force of 200 pound is acting at point A. So the given information in the problem are that we do have a force acting on this ring that is supported by these 4 cables. Okay? We want to find, if we apply this force of 200 on this ring acting downward, how much force each of these cable would carry. In other words, we want to find the magnitude of the force in all of these cables, okay? That's what we want to find. Of course, force of AB and AC are the same. Any questions? So this is an equilibrium of a particle in 3D. And this is the first step in any 3D problems that we will always follow. The first step is, when you're given a 3D problem, on the figure, write down the coordinates of all points. You need them to set up all the vector equations. Instead of chasing for these coordinates each time, if you write them down on the figure, makes your life a whole lot easier. Where it says D is along x-axis, this is given 80. So this is the coordinate of D. E is along the z-axis on the negative side of the origin. So you have 0, 0, negative 45. B is along the x-axis on the negative side of the origin and 17.5 from the origin. So it's negative 17.5, 0, 0. C is on the z-axis, positive side is 0, 0, 25. And A is 0, negative 60, 0. So always write those coordinates on the figure to make your job easier. Any questions? Please stop me at any step. Should we punish Arden not letting him in? Or, okay, Arden, you are late. Arden, you are 23 minutes late. Please show up on time next time. Okay, so that's the first step. The second step is we write down the equations of equilibrium. Summation of forces along x, y, and z equal to 0, okay? In order to apply these equations, what do these mean? That we need to find some of the components of each force. So the next step is to simply write the equations or vector equations for all forces. Okay, that's what we need to write down. Okay, so I start with the easiest one, that force of 200 acting downward, which I call that P. This is that force, right, of 200 acting here. So is acting along the y direction in the along that there, y-axis. Therefore, this is going to be the magnitude of that force, since it is in the negative direction, negative 200, times the unit vector of that direction. So that's the first force. How about the force in A, D? Okay, this is point D, 80, 0, 0. This is 0, negative 60, 0. So this is the force AD. So force AD is the magnitude of the force AD times the unit vector of that direction. So what is the unit vector? Tip minus toe. We have all these coordinates, so that makes our life easier. So it would be force of AD times 80 minus 0, 80 I, 0 minus minus 60, so it would be 60 J, 0 minus 0, 0, divided by 80 squared plus 60 squared, okay? And if you solve this, you see this would come out to be 100. So force of AD comes out to be the magnitude, which is unknown, times this, which becomes 0.8 I plus 0.6 J. So this is the force in AD, okay? Now, how about the force in AE? This is point, okay? This is point E, 45. This is point E, 0, 0, negative 45. So this is the force AE. Oops. This is E, okay? So with force AE is the magnitude of the force AE times the unit vector of AE. So that would be the magnitude AE. What is the unit vector? Tip minus tail. 0 minus 0, 0, 0 minus minus 60 would be 60 J, negative 45 minus 0, negative 45 K, divided by 60 squared plus 45 squared, square root of that. Simplify that. This is 75. So this will result in force of AE times 0.8 J minus 0.6 K. We have two more. Force in A, B. Okay, this is B, 17 and a half. So this is point B, which is negative 17.5, 0, 0. So this is the force in AB. Okay, so that would be what? That would be magnitude of the force AB times the unit vector of AB. What is the unit vector? Tip minus toe. Negative 17 and a half minus 0, 0 minus minus 0. So that would be FAB, negative 17 point and a half I, okay, plus 60 J, and that's it, divided by 17 point and a half squared plus 60 squared, and that is 62.5. If you simplify that, you get f of AB times negative 0.28 I plus 0.96 J. So this is the vector equation for AB. One more, and that is f of AC. Magnitude of it is the same as AB, but the unit vector would be the unit vector of AC, which is located here. This is point C here, located at 25. From here, this was 0, 0, 25. So the unit vector would be 0 minus 0, 0 minus 60, 25 minus 0. So it would be the magnitude of AB times, okay, point 92, point 60, I'm sorry, point 60 J plus 25K divided by 60 squared plus 25 squared. If you simplify that, becomes force of A, B times 0.92 J plus 0.38 K. Okay, so that's this, because this is 65.
Professor, is it supposed to be force of AC?
It is force of AC, but the magnitude of that is the same as the magnitude of AB. So for both of them, I wrote down magnitude of AB, because for
Can you explain how they're the same, please?
the problem statement says
Okay.
that the forces in these two are the same. That's from the problem statement.
Okay, thank
Any
you.
other? Sure. Any other questions? All right. Once we wrote all these down, the next step is the easiest one. You just write down summation of all x components 0. So this doesn't have an x component. This one does. This one does. This one doesn't. So you end up with this equation. 0.8 force of AD minus 0.28 force of AB is equal to 0. Right? Summation of y component is 0. This one has a y component of negative 200. This one has, and this one has. So all of them. So if you write those down, it would be negative 200 plus 0.6 F of AD plus 0.8 force of AE plus 0.96 force of AB plus 0.92 force of AB is equal to 0. Okay? And the last one, summation of forces along Z is equal to 0. So this one has no Z component. This one has, and this one has. And that would be negative 0.6 force of AE plus 0.38 force of AB is equal to 0. So you have 3 questions and 3 unknowns, where the 3 unknowns are the 3 forces that you're looking for: AB, AC, and AE. I'm sorry, AB, AD, and AE. So it's a 3 question, 3 unknown, but it's actually not that difficult, because from here you can find AE in terms of AB. From this one, you can find AD in terms of AB, substitute it in this equation, so you find AB. But anyway, regardless of how you solve this 3 question and 3 unknowns, you will end up with the magnitude of these unknowns that you've been looking for. F of AB comes out to be 77.1 pound. F, which is equal to F of AC. F of AE comes out to be 48.6 pound. And F of AD comes out to be 27 pounds. So we found the three unknown forces that the problem was asking for. Any questions? So the equilibrium problem, or the equilibrium, particle equilibrium in 3D, comes down to these simple steps. Write the vector equations for all forces, sum up all x components, set them 0, sum of the y component equal to 0, sum of the z component equal to 0, and that's it. You find those unknowns. All right? Okay, so with that said, let's move on to the next problem, next concept that we want to discuss. So let's see where we are again and where we are going. Okay, so you sure you have no question? Okay. So far, we have discussed the action of a force on a particle. If you have a particle A, you have a force acting on this particle. What does this force do? This force moves this particle along the direction that the force is applied. So the directional action of the force, which we call that translational effect, can be represented by this vector equation of this force. Or in other words, we said that a force that acts on a particle can be represented by a vector equation. And of course, if you have several forces, some of their actions is the result, right? Forces acting on an object are different now. They perform a different act than a force acting on a particle. Okay, if I have this is a particle and I exert a force to it, right? What does this force do? Simply move this particle in the direction that this force on my finger is applied. But how about if we are looking at the action of a force in an object where this object is connected or constrained from motion by having that connected to some point. So when you apply a force to an object, this force will try to move this object in the direction that it is applied, but also, since this object is constrained at some point, it will rotate this object about that point of connection. So that's what we want to describe or find out today, that what is the rotational, or how the rotational action of a force can be described. First of all, we refer to the rotational action of a force about a point or about an axis as the moment. So moment is a quantity that describes the rotational action of a force about a point or about an axis. How do we describe this mathematically, as we have done with a force? Okay. We say that if you have a force F, acting on an object, okay, we are interested in two things. Either we are interested about the rotation of this object about a point, or the rotation of this object about an axis. For instance, think of it like this example. If you have a car and your beautiful car, of course, has a hood, okay, and you lift this hood and you put a rod here to hold this hood, we are interested to know what is the rotational action of this force and the force of gravity of this hood about this axis of rotation. Why? Because that's how this structure is supported by these hinges. In order to design for these hinges, we want to know what is the rotational action that these forces cause. So that's the meaning of the moment about an axis. But if you're only interested to find a force, rotational force about a point, we call that rotational motion about a point. We're going to discuss both of these. So moment is either is to find the rotational action of a force about a point, or the rotational action of a force about an axis. And we're going to discuss both of them. Rotational action of a force about a point O is described this way. In order to find or describe or define the rotational action of this force about O, we simply connect this point to any point along this force, any arbitrary point A, and this vector that resolves, vector R, is called position vector. Once you obtain this position vector, moment of this force about point O can be defined by the cross product of this position vector and the force. That is, if you can set up the vector equation for this, the vector equation for this, you can fully describe the moment that is a vector resulting from this operation, because cross product of two vectors is a vector. The magnitude of this vector, we will see how we can find that, is all, it can be found as long as you have the component of this vector, right? And the direction of this operation can be determined based on the rule that you remember from physics or calculus, right-hand rule. If you have a vector A and another vector B, the cross product of these two, A cross B, is what? You put your fingers along the first vector in such a way that when you tilt your fingers, the tilt would be towards the direction of the second vector. And if you do that, then your thumb shows the direction of that product. So if you want to find forces rotation of this vector and this vector, right, you put your fingers along this, tilt them toward the direction of the second one and this. So because if you put your fingers this way, obviously, if you tilt your fingers, your tilting is in the opposite direction of this, so you cannot do that. So that's just, another way was tightening screw. If you or Faraday's law. But instead of using these silly approaches for 3D, is a whole lot easier to find the direction and the magnitude through a mathematical operation. A whole lot easier than remembering those tedious or sometimes confusing rules. In order to do that, you just simply set up a determinant whose first row are the unit vectors of the three coordinates. The second row are the x, y, and z component of that position vector. And the third row are the x, y, and z coordinate of the force. And then you try to expand this determinant. How do you expand a determinant? A 3 by 3 determinant? You remember that? If you don't, that's okay. This is how you do it. You consider the first row. Each element of this row has a sign. The first one is always positive, second one negative, the third one positive. If you have a more than a 3 by 3, this alternating signs continue. But we only are dealing with 3, so these two have positive signs and this one has a negative sign. In order to expand this determinant, in other words, find the value of this determinant, you do this. You consider the first element, and then you eliminate the row and the column corresponding to that element. So you end up with a 2 by 2 determinant. The magnitude of a 2 by 2 determinant is always obtained by performing this operation. You multiply these two and consider whatever sign they may have, subtract it from these. So this product minus the product of these two. So you just write I times Ry, okay, times Fz minus Rz times Fy. You repeat this by considering the second element, which is negative, eliminate the row, column corresponding to that, so you end up with this 2 by 2 determinant. That is, you have negative j times this times that, Rxfz minus Rzfx. Same thing with k. You eliminate the row and column corresponding to that. So you end up with this 2 by 2 matrix or determinant, and the magnitude of that would be plus k, which is positive, times Rxfy minus Ryfx. So this would be the moment of that force about point O. As I said, the outcome of a vector product, which is this, is, as you can see, a vector. This is the x component of that vector, x. This is the y component of that vector, and this is the z component of that vector, moment. This means if this is positive, this is x, this is y, this is z. This shows you how much or how this force is rotating an object about this point along x-axis. If this is positive, rotation is taking place in the positive direction of x. In other words, think of that tightening screw is moving this way, the rotation. Another way to demonstrate this rotation, to make it less confusing, some books use a double-headed arrow and show the component this way. This means the component of this moment along the x-axis, which is in the positive direction of x. For y, if this turns out to be negative, we show it this way, a double-headed arrow in the negative direction of y. And if this is positive, so this would be a double-headed arrow in this. The point is that the outcome of this operation is a vector, and these are its components. Therefore, the magnitude of that moment can be simply found by being a vector by the square root of the sum of the squares of the components. Okay? So this is the moment about a point. How about if you want to find a moment of a force about an axis? Remember that famous car? I want to find a moment of a force about an axis D. If you want to find a moment of a force that is acting on this object, for instance, along an axis, you write it like this: moment of the force about an axis. You can find the magnitude of that moment or the rotational effect about this as follows. You consider any arbitrary point you want along this axis, and you connect that to any point you want along F. Therefore, you find the moment of that force about O. We know by now this will be a vector. Then you set up the unit vector equation for this axis and find the dot product of that unit vector and this vector. The outcome will be a number, and that is the moment of this force about this axis D. So I went through the mathematical formulation for finding the moment about the point and about an axis, but to fully demonstrate that, so to make your job easier, let me go ahead with some examples, okay? So I will start with an example for a moment about a point. Any questions? So let me demonstrate first the concept of the moment about a point, okay? By choosing this problem from your book. So this is the problem. You do have a block given. Dimensions are given here. 2.5 meter, this is 2 meter. This is a point A, point B, point C. A cable is attached to point B that connects that to a point on this XZ plane, point D. Coordinates of this point are given. This dimension is 1.5 meters, and this is 2 meters. So the problem is stating that a force is acting along this cable, a force B, the magnitude of this force is given as 900 Newton. We want to find the moment of this force about point D. Or in other words, we want to find the rotation, point O. We want to find the rotational effect that this force causes about point O. Any questions? All right, so let's go step by step. In all 3D problems, I always strongly recommend that as a step one, you just write down the coordinates of all points that you have. That makes it a whole lot easier for you instead of chasing for these numbers as you try to solve the problem, you have them all in one place. So I would just simply write down the coordinates of all these points. This is 0, 2, 0. B is along the x-axis, and I'm sorry, parallel to the x-axis, this line, and you have the height, you have the distance. So this is 2.5, 2, 0. C is along the x-axis, 0, I'm sorry, 2.5, 0, 0. And O is 0, 0, 0. D is given with 1.5. No Y because it's on XZ plane. And so I wrote all the coordinates of all the points given. The second step is what? You want to find the moment of this force BD about point O. So write down the equation that you need to solve or set up. How do you find the moment of a force about point O? I said that you can just simply connect that point to any point along the direction of this force. But we only have the coordinates of these 2 points. So you can either consider this or you consider this as your position vector. Okay? So this would be simply R cross that force BD. So in order to set this up, you need to write the vector equation for both. What is the vector equation for R? Let me consider this as the position vector. Does not matter which one you choose. This is easier because it's on XY plane. So coordinates of this minus that, you simply write that, you see that this would be what? If this is 2.5, I plus 2j plus 0k. How about the vector equation for f of BD? That is the magnitude of BD times the unit vector of BD. And what is that unit vector of BD? Tip minus tail. So 1.5 minus 2.5, negative 1. I. 0 minus 2, negative 2j. 2 minus 0 plus 2k divided by square root of 1 plus 4 plus 4, which becomes 9. So this is 3. So this vector equation becomes simply negative 300i, negative 600j plus 600k. So this is the vector equation for the force. This is the equation for R. So the moment is simply the cross product of these two, which means you set up this determinant I, J, K. Second row is R, that is 2.5, 2, 0. Third row is force, negative 300, negative 600, 600. So all you need to do is to simply expand this determinant. How do you expand it? I eliminate the column, row corresponding to that. So this would be 2 times 600 minus 0 times this. So it'd be 1200 times I. For J, eliminate this, eliminate that. So you end up with this. But J has a negative sign. So remember, you have then 2.5 times 600, which is 1500 minus this times that 0. So this is J. How about for K? Eliminate this, eliminate the row. You have positive. You have 2.5 times negative 600, that is negative 1500, minus this times that, which is 600. So this ends up to be negative 900. So the moment equation comes out to be what? Would be simply negative 1200 I minus 1500 J minus 900 K. What does that mean? That means this moment of this force about O has a positive, causes a positive rotation. If I want to show that with double-headed arrow, that is, this is 1200 Newton meter rotation. Rotation about Y is negative. That is, this is causing a 1500 Newton meter rotation in this way. Imagine this way, downward. And about K, also negative. That is, it is causing a rotation of 900 Newton meter in this direction. But what is the magnitude of this moment? Magnitude is easy. Magnitude would be the square root of the sum of these squared. Okay, 1500 squared plus 900 squared. If you calculate that, you'll end up with 2121 Newton meter. Any questions? As easy as that. Could not be easier, right? Find the moment about an axis or finding a moment about, moment about an axis, of course, we'll discuss it next time, but that's how you find the moment about a point. Any questions? If not, if you want to see me during my office hours, you're welcome to, and I'll be there in half an hour. Otherwise, have a great day.